I received a number of questions from students about the take-home midterm. Some of you may not be aware that there is this set of notes, engine dynamics, on Blackboard, where we have the equations for the slider displacement as a function of crank angle, for the centric slider crank. You have the equation to convert from slider displacement to the angle of the crank. You have velocity, you have acceleration of the slider equations. There's also the equation that lets you go between volume and slider displacement, pi d squared over 4. That'll be the area of the piston. There's also a MATLAB code does FFT of the piston displacement. I ask you to do FFT of the piston acceleration, so you'd need to replace the equation for S with the equation for in the MATLAB code was the equation for acceleration. Okay, now for the spreadsheet, the startup values are the digitized PV curve. The time column is generated later using, sorry for the background noise, is generated for once you get the contiguous theta produced. And as you can see, it uses omega, the omega being the angular velocity, knowing the angular or rather RPM of the crank. Okay, so S is function of V, equation from the notes. Theta is function of S, equation from the notes with the R cosine. The problem is R cosine returns values between 0, the way it's working between 0 and 180. But so if I'm looking at the values just as ordered values, they stop, they go 0, 180, and then go back. You want, instead of going back, to continue. So this value should be in extension, this should be in extension, and that's why. So if I'm looking at the corrected angle, and I'll show you how that corrected angle you can get it. So if I look at the corrected angle, the way it looks is like so. So it goes past 180 all the way to 720 degrees. That's the 720 degrees, 2 crank rotations, full cycle of a 4-stroke engine. So how am I doing this? Using an equation. So the equation is actually no. First one stays the same. I thought I missed something, but no, it was a purpose. So I'm using the equation. You can do it by hand, or you can use this equation that looks at the value and 2 successive values, and if they continue to increase, then they stay unchanged. But if the next value is less than the previous value, that value gets subtracted from 360, and this is going to work up to the second 180, that up to 360. So this is the last one that it works. When I get to past 360, I need to, in addition, add 360. Again, I figure out this is the equation to use. You can do it by hand. It's a matter of when you see the values going back, you need to subtract the respective value from 360. And then you need to subtract that value from actually 720. So I could have replaced this with Let's see if it works. So if instead I here say 720, does it work? Actually, no. So it was for a reason. I was just experimenting live, but it was a reason I made my equation look the way they are. Going back from degrees to radians, that was needed for later calculations. Again, trig functions in Excel, they need the argument to be supplied in radians. This is where the time gets calculated. When I have the angle, the corrected angle, contiguous, going all the way to 720, turn to radians and then multiply by, or rather divided by angular velocity gets you the time. Okay, so you have the distance divided by velocity gets you time. Likewise in rotational motion. The equations for S as function of theta. See the notes equation as so velocity of S is function of theta, acceleration of S function of theta. Force upon the piston is nothing but the pressure multiplied by the area of the piston. Torque, use the principal virtual work, so you have the velocity of the in meters per second. You divide by omega, and then so equation for torque. And then you do trapezoidal integration to calculate the average torque. So the sum of, where's the average? The average, okay, work per cycle W, that will be the sum of trapezoids, and then the average would be divided by the work per cycle divided by the length of the cycle, 4 pi. I have a full column of average torque, and it served to produce this line. And then what I'm doing, I'm subtracting the average value from the original torque, and anything that is negative gets changed to 0. So this bottom graph is nothing but a representation of everything that's above the T average line. Okay. And I'm doing this using also an equation. So it says if the difference is negative, then it's 0. If the difference is not negative, it just uses the value. Okay. And one more trapezoidal integration, and that gets you the sum of trapezoids gets you the delta E, the area above the torque curve, and or delimited by the torque curve, and the average line and area that's above. So I guess, and with this, knowing delta E, can calculate the flywheel moment of inertia. And this is it. I'm going to stop the recording. Hope that this helps with completing the assignment.